this video, we're going to set the stage for the fundamental theorem of calculus, part 2. It gives us a very slick way to calculate signed areas under curves by asking ourselves a totally different question. Remember, right now, to calculate the signed area under a curve, we can only really estimate with the Riemann sum. And then we can take a limit of that Riemann sum as the number of rectangles goes to infinity, but that's icky. And the fundamental theorem of calculus provides a very, very, very clever way to answer that limit by doing a different question. Okay? So let's have some intuition here. So very, very basic example. Suppose I'm on cruise control and I'm driving at a constant rate of 50 miles per hour from 1 to 3 p.m. I want to graph the distance function, right? So let's label these axes. Here's your time in hours. Here's my distance, and it's in miles. Right? And so between at 1 hour in, I've traveled 50 miles. 2 hours in, I've traveled 2 50s, 100 miles. 3 hours in, I've traveled 3 50s, 150 miles. The slope of this line is up 50, going from 50 to 100, up 50 to the right 1. So I just want us to graph the distance function, my position function, over that closed interval. Now the velocity of my car, I'm going 50 miles an hour at a period, right? Constant, meaning I'm not accelerating or decelerating. This is a very idealized situation here on purpose. My velocity is always 50 miles per hour. The derivative of 50t is just 50. It's a constant 50. My velocity from time 1 to 3, 1 o'clock to 3 o'clock, say, and here I'm graphing the velocity in miles per hour. It's always 50. Okay? So I want us to now use geometry to find the area under the velocity function from t equals 1, from 1 o'clock to 3 o'clock. So I'm looking at finding this signed area. He's always going in the positive direction. He's not double backing on himself. This happens to all be positive. This area is representing that distance that he's traveled between 1 and 3, that net change in distance. So the area of this rectangle, right, that area is base times height. The base here is 2 hours. The height is 50 miles per hour. Your hours are canceling, and you're ending up with 2 times 50. You're ending up with 100 miles. That's that blue area is representing that net change in position, that distance traveled here. He's not double backing. This is 100 miles. Now let's go back to my distance function, and I want to find a difference in the heights here of d3 minus d1. All right, so let's go back up to that graph. Here is, I'm going to scooch my miles down. All right. So D3 is 150. And D of 1 is 50. Right? When T is 1, D is 50. D of 1 is 50. When T is 3, D is 150. D of 3 is 150. So let's go ahead and subtract those. The difference in those heights, 150 minus 50, will lo and behold be that same number, 100 miles. Units all match here too, right? So D3 is 150, D of 1 is 50, D3 minus D1 is 150 miles minus 50 miles, which is 100 miles. So, the answer to questions C and D are both 100 miles. I did an explanation point because it's so cool. They are the same. So, why does this matter? Well, if I'm asked to find a complicated signed area under a curve, the area between a curve and the x-axis, and geometry won't work here, what can I do? Instead of taking a limit of that Riemann sum and let the number of rectangles go to infinity, I'm going to ask myself a different question. What's an antiderivative for this function? Here's the graph of the velocity is always 50. What's an antiderivative for that function? If I can find it, and that's an if, but if I can find it, here's that antiderivative, then I can just evaluate it at the endpoints. The derivative of what function is 50? The derivative of 50t is 50. And I can just subtract these heights, d of 3 minus d of 1. Right? This is awful, awful beautiful. What's going on right here? The slopes up here are the y values, the heights down here, right? When you sketch a graph of the derivative, you're going point by point and you're saying, what is the slope of the tangent line there? Here we have a nice example where the slope is always 50, which is why when I'm graphing the slope, we have that the velocity is always 50, just doing it over a particular interval. And the area, really that signed area, down here, that area of 100 miles, and yes, I'm saying miles, matches the difference in these heights, d3 minus d1. Super beautiful. So that is one of the main reasons why we want to be able to come up with antiderivatives. If you are looking for a complicated total, and in your Calculus 2 class, you're going to look for all sorts of complicated totals, but you're going to start by finding complicated totals of areas between curves and the x-axis. If this area is complicated, this one's not, but if this area is complicated, you can instead ask yourself a different question that has the same answer. What's an antiderivative function for the one that's been given to me? Let me just evaluate that at the endpoints. and take the difference. Super, super elegant. We're going to investigate this more, but we've set the stage. Thank you for watching.